Acoustics of building. This was the subject matter of our previous video. And as I have told you that the whole concept of acoustics of building will be dealt in two lectures, not in only one. And you have seen the first part of the lecture on this acoustics of building. In fact, in that first part of the lecture on acoustics of building, I have only introduced you some basic facts regarding this acoustics of building. First of all, I have introduced you a very important term which is called reverberation. What is this reverberation? Actually, this reverberation plays a vital role in case of acoustics of building, and we have already learned it. When you say a reverberation, you know, if there is a source of sound in a room and there is an observer also inside that closed room or enclosure or closed hall, then the sound wave produced by the source suffers multiple reflections from the different walls, floors and ceilings, and after suffering multiple reflection, the observer receives it. But if the source is cut off, even after removal of the source, the observer feels the intensity or energy of sound wave. That is called persistence of hearing. Actually, this phenomenon of persistence of hearing is known as reverberation. And you have seen this in our first lecture. Here S is the source and this is the observer, and these dotted lines represent the sound wave emitted from this source, and after suffering multiple reflection from different walls or ceilings or floors, it is received by the observer. Okay? And after knowing about the reverberation, you have also learned the period of revolution. And you know, this period of revolution is actually the time interval during which the intensity or the energy density of the sound wave falls to its audible value, let us say E. E is the audible value of the energy density. It means if energy density will be less than this E, the sound will be not audible. So if the energy density in the room after the removal of the source of sound falls to this audible value E from a value of 10 to the power 6E, that is 1 million times greater. So if the initial energy density is 10 to the power 6E and finally it becomes E, where E is actually the least value of energy density, that will be audible. So this is also called threshold value of audible density. Then the time taken in falling the energy density from this value 10 to the power 6E to E, that is called reverberation time or period of reverberation. Okay? And what is the expression for this period of reverberation? Actually, that was obtained by Sabine after a series of experiments, and he obtained that this T is given as K times V over A, where K is a constant and V is the volume of the enclosure or volume of the room or hall, and A is total absorption power. Actually, this result is known as Sabin's formula or Sabin's law. Actually, these three things we have learned in our previous lecture. Now, the aim of this second part of the lecture on acoustics of building is actually to discuss the growth and decay of energy or energy density or intensity of sound wave in a hall, in a closed enclosure. And our aim is also to derive this Sabin's law. Okay? So, how the energy density grows in a hall, how it decays, and how we can obtain the Sabin's formula, today we are going to see. Okay? So, now let us first of all see the growth and decay of sound in a live room. And among these two processes, first of all, we are talking about the growth of sound wave. Okay? When you say a live room, that means the room is not dead. Dead room means there is nothing inside the room. Okay? The room is empty. But when you say live room, that room contains so many things like chair, tables, and so many things. That is called a live room. That is a room in which some person is living. Okay? In fact, it is found that the absorption coefficient of the materials of the walls of a live room is very small, and its value is less than 0.4. Now, since the absorption coefficient of the walls of a live room is small, so there will be an increase in loudness of sound due to reverberation. If the source of sound is not cut off, it is present, then actually the intensity of sound wave or the energy density of the sound wave will increase with time in the live room. Okay? Now, suppose that there is a source of sound which produces a constant output. It means its output power is constant. Let us say this is of 40 watt, this is of 100 watt, this is of 200 watt. So its output power is constant. Okay? Now you know when this source will produce sound wave, then due to reverberation, initially the energy density of the sound will increase, and after some time it is found that the energy density attains a maximum value which does not change with time. It means an steady state will be reached when the energy density in the room becomes constant. Okay? Actually, in this section, growth, our aim is to find the expression for the energy density or the intensity of sound inside the room at any time t. Okay? At any time t, we are going to find the expression for intensity. And that expression actually will give the law of growth of energy density or growth of intensity. You will see that actually the intensity or the energy density in the room when the source of sound remains working, it is not cut off, then it increases with time exponentially. But if you will keep the source sounding for a long interval of time, it does not mean that continuously the intensity will increase. But you will see after some time there will be a steady state, there will be a situation of saturation. The energy density or intensity will be saturated at a particular maximum value. Okay? But how the intensity changes with time, what is the law which governs the variation of intensity with time inside the live room, that is actually found by assuming three basic facts, or on the basis of three hypotheses or three assumptions, you can find this relation. And what are those assumptions? I have mentioned here. You can see the first assumption says the source emits sound energy at constant rate. It means what is the value of energy emitted by the source of sound per second, that is constant. Okay. Just for example, as I have told you that our source is of power P equal to, let us say, 400 watt. It means this source emits 400 joule energy per second, and this is fixed. Okay. And this source just acts like a point source, and you know, if the source of wave is a point source, it produces wave and which will actually transmitted almost in all directions. So here we will consider that the sound wave produced by the source is propagated in all possible directions. Okay. And our third assumption is that the distribution of energy inside the room is uniform. It means energy density at any point inside the room is constant. It is not non-uniformly distributed. Energy distribution is uniform. So energy content in unit volume in any region of the room will be same. So these are the basic three assumptions on the basis of which we are going to find the law that governs the growth of energy or energy density or intensity in the live room. Okay. So now how we can find it, let us see. In fact, see this figure. Actually here in this figure I have shown this, you can see this ds, which is an elementary surface on a wall. For example, if this is a wall and this is your elementary surface, which I have shown here in this figure by ds. Okay. And we also consider that from this elementary surface at a distance r, there is an elementary volume dV inside this room. Okay, are you getting the things? ds is an elementary surface on the wall, or you can say that we consider a very small element of the wall. And inside the room we consider an elementary volume which is dV, and at this surrounding this point P, and it is this dV is at a distance r from this element, from this surface element, you can say. Okay. Now we consider that this zx, this surface is lying in xy plane. If ds is lying in xy plane, then you know z axis will be normal to its plane. Okay. And this z axis, which is normal to the plane of this surface, that makes an angle theta with the position vector of this point P, surrounding which you have considered this elementary volume. Okay. So the direction of this r makes an angle theta with the normal drawn to the elementary surface ds. Okay. Actually, here we will make our calculation in a spherical polar coordinate system. In fact, we have to find how much energy is emitted by the source per second, and how much energy is absorbed by the surface per second. And for that, first of all, let us see that at the site of the elementary volume dV, that is at point P, this surface you can see is making a solid angle which I have marked by this d omega. D omega is the solid angle which is subtended by this elementary surface ds at the point P, or you can say at a distance r, making an angle theta with the normal to the surface. Okay. Now, as I have told you that we will make our calculation in a spherical polar coordinate system. And can you say what is this elementary volume dV in a spherical polar coordinate system? A spherical polar coordinate system means r, theta and phi. You know, this is given by dr into, actually this length is in fact dr. Okay, this length will be r d theta, and this length is r sine theta d phi. Okay, so dV is dr into r d theta into r sine theta d phi. Okay, and you can say that this is simply r square sine theta d phi times dr. This is the volume element dV. Okay, and what is this d omega, which is the solid angle subtended by this surface on at point P? You know, by definition of solid angle, d omega is given by ds cos theta by r square. Okay, this is the solid angle made by this surface at the point P, where the elementary volume is located. Actually, I have mentioned these facts here. You can see that dV is given by this expression, and the solid angle made by this surface ds at the elementary volume dV, this equal to this much. Okay. Now, let us consider that this E is the energy density in the room at any time t. When you say energy density, what does it mean? It means E is the amount of energy distributed in unit volume of the room at any time t. Also, you can say that this E is the instantaneous energy density. And you know, as our assumption is that energy distribution is uniform. So, at this time t, at any position inside the room, energy density will be same, and that will be E. Okay. Now, you can see, since E is energy density, which means energy content in unit volume, so in unit volume, the energy content is E. So, what will be the energy content in this elementary volume dV? This will be simply E times dV. So, E dV represents the energy content in volume dV at time t. Okay? And now see, actually our aim is to find how much energy is incident per second on this elementary surface ds. Okay, and for this you have to use the idea of solid angle. You know, if I will ask you a question that if there is a closed loop, not a surface, closed loop, this is a loop, and this loop may be of any shape and size, and there is a point P inside it. You know, loop is a line, okay, and so this loop makes plane angle, not solid angle, at this point P. Can you say what is the total plane angle subtended by a closed loop at an internal point? Definitely you have an idea. The answer is 2 pi. It means any closed loop makes total plane angle 2 pi at any point inside the loop. In fact, similarly, if now you are talking about a closed surface, this is a surface, not a loop, but closed, okay, and there is a point P inside it. Can you say what will be the total solid angle subtended by this closed surface at this point P? Definitely you can say. The answer is 4 pi st radian. or 4 pi unit you can say. So this is a general fact that the total solid angle made by a closed surface at a point inside the surface is 4 pi unit. Okay? And outside of the closed surface, the total solid angle is 0. Okay? So, if you treat this elementary volume dV just as a point source, and it is inside the closed in a closed room or closed hall, okay, so the energy will be emitted from this elementary volume almost in all directions. If I will ask you that what is the solid angle in which the energy from this elementary volume will be emitted, answer will be 4 pi, because you know that the energy there is a 4 pi units of solid angle surrounding a point P. Okay? So the energy E dV, which is contained in this elementary volume, that will actually emit the total energy E dV through the solid angle 4 pi. Now let us see how much energy or which energy will fall on this elementary surface ds. Definitely you can say that from this point P, actually at this point P your elementary volume is situated. From this point P, the amount of energy which propagates through this solid angle d omega, that will be incident on this elementary surface. So if your aim is to find the amount of energy falling on this elementary surface ds from this element of volume dV, you can use the idea of this solid angle. You can see through a 4 pi solid angle, the total energy emitted will be E dV. Okay? So through unit solid angle, what will be the emitted energy? That will be E dV divided by 4 pi. And therefore, what will be the energy emitted through the solid angle d omega? That will be equal to E dV divided by 4 pi times d omega. This much energy will be emitted from the elementary volume through the solid angle d omega. But this angle emitted through the solid angle d omega will fall on the surface ds. So the energy falling on surface ds and energy emitting through solid angle d omega both are equal. Okay? And that will be equal to E dV divided by 4 pi times d omega. Okay? So I have made such a calculation here. You can see energy crossing through solid angle 4 pi is E dV. Okay? Is it clear? And so energy crossing through unit solid angle, that will be E dV by 4 pi. And therefore energy crossing through d omega solid angle, this will be E dV by 4 pi times d omega. Okay? But as I have told you, that energy falling on ds from the element dV, that is simply equal to the energy emitting through the solid angle d omega. So that amount of energy which falls on the surface ds from the element dV, that is given by E dV divided by 4 pi times d omega. Okay? Now let us substitute the value of dV and d omega, which already I have defined earlier in a spherical polar coordinate system. So after substituting the values of dV and d omega in a spherical polar coordinate system, this expression becomes E times r square sine theta d theta d phi dr over 4 pi times ds cos theta over r square. Okay. This is the energy falling on the surface ds from the element dv. Now, if your aim is to find the rate at which energy falls on this ds, it means how much energy will fall per second on the wall, then how you can find it? For this, if you are talking about the total wall, total surface, then you have to actually integrate this result between the appropriate limits. Here, integration will be done with respect to the three variables. You can see the variable theta, phi and r. Okay. So, when we will integrate this expression for theta between 0 and pi by 2, these are the limits of theta. For phi, the limits will be 0 and 2 pi. Upper limit will be 2 pi. And for r, what will be the limit? 0 and v, where v is the velocity of the sound wave. Why you have taken the upper limit of r equal to v? Because we are going to find the rate of fall of energy. It means energy falling per second. And you know, in 1 second, anything covers a distance equal to its velocity. So in 1 second, sound will cover a distance equal to its velocity v. Okay. So after integrating this result, then the energy falling per second on ds, or the rate at which energy falls on it, not on ds but now per second on wall, you can say total wall. Okay. No, sorry. No. On ds is correct. Total energy falling per second on ds. After that we will find the total value. Till now we are calculating the total energy falling on this ds per second. Okay. And as I have told you, for that you have to integrate this result between the appropriate limits of the three variables theta, phi and r. And what will be the appropriate limits I have just discussed. So you can see this will be in E ds over 4 pi. This is actually a constant factor. And integral with respect to theta, and the integrand will be sine theta times cos theta from 0 to pi by 2. Then integral from 0 to 2 pi d phi integral over dr from 0 to v, where actually v is velocity of sound. Why I have taken v? I have already explained that this is actually the distance covered by the sound wave in 1 second. Now, you know, integral of d phi between limits 0 and 2 pi, that will be 2 pi. Integral of dr between limits 0 and v, that will be v. Okay. And what is this sine theta times cos theta? This is actually sine 2 theta divided by 2, because when you will take a factor 2 in denominator and also in numerator and denominator, then 2 sine theta cos theta will be sine 2 theta. Okay. And so its integral will be minus cos 2 theta by 2. So this result is E ds v divided by 2 into 2 and this much. Now after substituting the limits, your result will be 1 over 8 EV times ds cos 0 minus cos pi. But cos 0 is 1 and cos pi is minus 1. So this minus times minus will become plus. So 1 plus 1 will be 2. Okay. So this result is finally 1 over 4 EV times ds. E times V times ds. So this is the an amount of energy that falls in 1 second on the surface ds. Okay, on the surface ds. Now, as you know, energy falling per second on unit area normally, that is called intensity of the wave. We have already discussed intensity of sound wave in previous video in very detail. So this expression actually measures the amount of energy falling on surface area ds in 1 second. Now if you will take ds equal to 1, that is energy falling on unit area in unit time, that is called intensity. So the intensity of the sound wave here will be 1 over 4 EB. Okay, because for getting this intensity you have to divide that amount of energy by the surface area. So I is equal to this much at any time t. Why any time t? Because here this E is variable. Energy density in the room is changing. Although at a particular moment it is throughout same, everywhere same, but with time it will decrease. Or it will, in this case it will increase in fact, because source is continuously emitting the wave. Okay. Now this energy which falls on the surface, you know, a particular amount, a particular part of the incident energy will get absorbed by the surface, will be absorbed by the surface. Okay. And what amount of the energy will be absorbed, that depends on the absorption coefficient. And how this absorption coefficient is defined, you know, if you consider that A is the absorption coefficient, then it may be defined as rate of absorption of energy by ds divided by rate of incidence of energy on ds. Here rate is not needed, but here in our calculation we are going to find the energy absorbed by the surface in 1 second. So I am talking about rate. Okay. Therefore, from this result you can see rate of absorption of energy by ds. What will be this? This will be A times rate of incidence of energy on ds. But you have just calculated that the energy incident on the surface ds per second is equal to this much. This is the amount of energy. Okay. So we will put this expression for the rate of incidence of energy on ds. Therefore, the amount of energy absorbed by the elementary surface ds in 1 second, which is called rate of absorption of energy by ds, that is given as A times 1 over 4 times E times V times ds. Okay. This is the amount of energy that is absorbed by this elementary surface ds in 1 second. Now you can easily find what will be the total energy absorbed in 1 second by the walls of the room. And for this you must integrate this result. So the rate of absorption of energy by the entire surface, that is wall of the enclosure. What will be that? That will be integral of this much. That is integral of A EV ds divided by 4. Here EV divided by 4 is a constant factor. This will be outside of the integral. And inside the integral there is A ds. But you know, in the previous lecture I have told you that the total absorption power A is given as A1 times S1 plus A2 times S2 plus so on. Here actually A1, A2, these are actually the absorption coefficient at different points. S1, S2 are the, in fact, surface area for which the absorption coefficient are A1, A2 and so on. And so this is in fact AI times SI, summation over AI times SI. But if the surface is distributed in fact continuously and A has a constant value, then actually the integral of A ds will give the measure of total absorption power. In that case, this summation will change into integration. So instead of integral of A ds, now I am writing this capital A, which actually represents the total absorption power. Okay. So the total energy absorbed in 1 second by the wall, that is given by EVA divided by 4. Okay. EVA divided by 4. This much energy is absorbed. Okay. And what will be actually the rate of emitted energy, that you can also find. Now let us consider that V is the volume of the enclosure. V is the total volume of the enclosure. And you know that E is energy density, which means this is energy contained in unit volume. So what is the total amount of energy contained in volume V? That will be simply V times E. So V into E, this measures the amount of energy distributed in the room at any time t. Why any time t? Because E is the energy density at time t. Mark it. Now, as the energy density changes, E changes, so in this case there will be a change of total energy in the room. And as E will increase due to the continuous working of the source of sound, so the energy in the room will get increased. And at what rate energy increases? That is, what is the rate of increase of energy? It means how much energy is increased in 1 second. That can be found simply differentiating this VE with respect to T. So d dt operated on VE, which will be equal to V times dE by dt, because here V is the total volume which is constant. This is volume of the room. So this V into dE by dt gives the rate at which energy grows in the enclosure. Okay. So let us see. Now, actually two phenomena are taking place in the room. Energy in the room is increasing at this rate, defined in equation 3. And energy in the same room is absorbed at this rate. Okay. And our source which produces the sound has a constant power output. If you consider that P is its constant power output, what does it mean? It means this source emits a power P or produces a power P in the room constantly. It means in 1 second, the energy provided by the source in the room is P. And actually that energy is utilized in two forms. This V times dE by dt, this is a part of energy P which appears in the room. And this EVA divided by 4, this is another part of this energy P which is get absorbed. So if you will add these two, you will get the total energy produced by the source in 1 second. This is actually nothing, this is simply the principle of conservation of energy. So you can say from energy conservation principle, rate of growth plus rate of absorption, that will be equal to rate of emission. Emission means source जिस पावर को emit करता है. Okay. And I have considered that our source produces a power P constantly. Okay. Therefore, mathematically you can say that this V times d by dt plus EBA by 4 is equal to P. And so, our aim is to find E. So, we will solve this differential equation. But for solving this differential equation or finding the value of E as a function of time, we have to integrate. But before that, you can see this equation must be cast into a form so that integration can be done easily. And for this, let us bring this second term in LHS in the right hand side. And then your result will be V dE by dt equal to this much, P minus EBA by 4. And so V dE divided by P minus EBA by 4, that's equal dt. Now this equation is integrable form and you can easily integrate it. So let us integrate. We consider that at t equal to 0, the source is switched on and we are making the calculation at t equal to t. Okay. At t equal to 0, source is switched on and we are going to make our calculation at any moment t. So now let us integrate. V is constant, so this will be integral dE by P minus VA by 4 times E, and limits for E will be 0 to E. Okay, and integral of dt from 0 to t. Now you can see that if you are talking about an integral like this, dx divided by a minus bx, what is this integral? This is minus 1 over b log a minus bx. So utilizing this formula, you can see at the place of a there is p, at the place of b there is va by 4. So using this formula of integration, you can write that this integral is minus 4v over a small va. Here capital V you can see is volume and a small v is velocity of sound. And log of P minus VAE divided by 4. Okay, and limits are 0 to E. Now, when you will put the limit, upper limit, then at the place of this E there will be E, so this factor will remain same. And when you will take the lower limit 0, this second term will become 0 and that will be simply minus log P. But you know log A minus log B is log A by B, so this LHS can be written as log P minus VAE over 4 divided by P, and that is equal to minus VA times T divided by 4. And therefore you can write this P minus VAE by 4 by P equal to E to the power this much. But when you will divide both of the terms in numerator by this P, your result will be 1 minus VAE divided by 4P. Okay, and that's why VAE divided by 4P, this is 1 minus exponential raised to the power minus VA divided by 4B times T. And therefore, E is equal to this much. This is the energy density in the room at any time T. Okay. Now see this result seriously, and you can see at t equal to 0, what will be the value of E? Easily you can say this will be this 4p divided by AB times 1 minus 1. Why this second one? Because there will be E to the power 0 and that is 1, and so this value is 0. So at 0 time, the energy density in the room E is 0. But due to the presence of this minus sign and this minus, you can easily see from this result that as the time increases, the value of E will increase in exponential manner. It will You can say that E is increasing with time exponentially or asymptotically. Now, when T will become maximum, if you consider that T tends to infinity, then E will have its maximum value. And what will be that maximum value? You can see. When T tends to infinity, E will be maximum, and this will be 4P over AB times 1 minus e to the power minus infinity. But you know, e to the power minus infinity is 0. E to the power minus infinity, this is 1 over e to the power infinity. And you know, e to the power infinity is infinity, and when you will divide this 1, which is a finite number, by this infinite, result will be 0. So this is 0. And that's why the maximum energy density in the room, you can say, is 4P over AB. Okay. So now, in this expression, instead of this 4P over AB, you can write this E max. Okay. And therefore, finally, we get that at any time t, the energy density in this room is given by E equal to E max times this much. Okay, E max times this much. Now you can see the variation of this E in against of t here. At 0 time, this energy is density is 0, and as the time increases, energy density grows exponentially or asymptotically, but after a long time, it becomes constant. It acquires the steady state value, and that steady state value is 4P over AB, which is actually the maximum value of A. Okay. So this is the law of increase or growth of energy density or in the live room. Now, you have seen earlier that this energy density is directly related to intensity. I equal to EV divided by 4. So if you will multiply this equation 5 both sides by V by 4. So what will be that? In LHS there will be EV by 4. In RHS there will be E max times V by 4 and times 1 minus e to the power minus VAT are divided by 4. But now you can write EV by 4 equal to I, and similarly EV max times V divided by 4 will give the maximum value of intensity. So in the similar manner, the intensity of sound wave also grows in the live room. Okay, and you can write I equal to I max times 1 minus e to the power minus VAT divided by 4. So if you will plot a graph of I in against of t, you will obtain the same curve of same nature. Okay, I have mentioned here that this I max is equal to this much from this result. Okay, and therefore E max is given by 4I max over B. Okay, so this is the law of growth of energy or energy density, or you can say intensity in a live room, when the source of sound continues producing sound. Okay, but now we will talk about the another process which is called decay of sound. When we will talk about decay, now let us consider inside the room when energy density becomes maximum, that is there is a situation of steady state, or intensity is at its highest value, maximum value. In that situation, now let us say that this is our source of sound, it is removed, or it is cut off, or it is stopped. Then what will happen? Don't think that when the source of sound will cut off, energy density or intensity in the room will fall to zero suddenly or immediately. It is a wrong notion. Energy density in the room or intensity in the room will not fall to zero suddenly or abruptly or immediately, but it will take a long time before the intensity in the room will become zero. This is actually called the decay of energy. Okay? Just you study in electrostatics the charging and discharging of a capacitor. In electromagnetics, you study the growth and decay of current in an inductor. All these phenomena of electricity are identical to this. Okay? So in this case, as the source is removed or source is stopped, so can now the source produces energy? Answer is no. So simply in energy conservation equation, now you have to take P equal to 0. See here, when we have made the calculation for growth, how you have done the calculation? Taking the energy conservation principle under account. But as now the source is removed, so in that condition, this P will be 0. And the sum of rate of growth and rate of absorption will be 0. Why? Actually, in that condition, there will be not a growth of energy density, but there will be a decay of energy density. Okay? So, one term in this expression will be positive and another will be negative, and their values will be same, and so their sum is 0. Okay? So, in this condition, when you will apply the energy conservation, your equation will be V dE by dt plus EVA by 4 equal to 0. And therefore, V dE by dt is equal to this much. This is a very simple equation, and you can arrange the terms in this way. dE by E equal to minus VA by 4V times dt. Now let us integrate. You know, when we remove the source or stop the source emitting power, let us take that time 0. So you shut off the source at 0 time, and you are now making the calculation at t time. So the limits for time will be 0 to t. But when we set up the source, can you say what was the energy density at that moment in the room? That was at its maximum value, because I have told you when energy density is at steady state value, then the source is removed. Therefore, corresponding to time t equal to 0, the value of the energy density will be E max. Okay? And let us consider at any time t, the energy density in the room is E. We consider it. So the limits for the integration of dE by E will be E max to E. And you can see this will be simply log E by E max, and that is equal to minus VAT divided by 4. And therefore E over E max, this will be exponential raised to the power minus VAT over 4B. And therefore E is given by E max times exponential raised to the power minus VAT over 4B. This equation actually gives the law of decay of sound energy in a live room. Now again, you know, we can write this equation in terms of intensity simply multiplying both sides by V by 4. So if I is the intensity of sound wave at any moment t in the room, then I in this case is given as I max times exponential raised to the power minus VAT over 4B. Now it is obvious from this result, if you will take t equal to 0, you can say what will be E? E will be equal to E max times e to the power 0, but e to the power 0 is 1, so at initial moment energy density is maximum. Similarly, you can say at initial moment intensity is also maximum. But when t tends to infinity, then this e to the power minus infinity will become 0, and that's why e or I both will tend to 0. So the variation of this e, or you can say I, in against of t is like this. Here you can also write the value I max. Okay. So at initial moment E is E max or I is I max, and as the time passes this exponentially decreases, and when t tends to infinity, then E or I becomes 0. So it is clear that after removing the source, or after shutting down the source, or after cut off of source in the live room, the energy density or the intensity does not fall to 0 immediately, but it takes a time in falling to 0. Okay. So I have written that it is clear from equation 8 and 9 that when source is removed, energy density and intensity does not fall to 0 immediately, but falls exponentially. Okay. So after knowing the process of growth and decay of energy in a live room, now we are at the verge when we can talk about the Sabin's formula. What is this Sabin's formula? You know, Sabin's formula actually determines the expression for the time period of reverberation. So applying the basic definition of period of reverberation, you can easily find Sabin's formula. Okay? You know, what is time period of reverberation? You have already discussed this in the first part of the video, and today I have repeated that. If the initial intensity or if the initial energy density is 10 to the power 6e, and the final energy density is E, which is actually the threshold energy density, then time taken in falling energy density from 10 to the power 6e to E is called time period of reverberation, capital T. So let us see. As we have seen that at time t the energy density E is given by E max times exponential raised to the power minus VAT divided by 4. So when you will take E max equal to 10 to the power 6e, if you take, then after this time capital T, the energy density will become this E. So in this equation, when you will take E max equal to this much, and this E is equal to E, then you must take capital T at the place of this time T, that is the time of reverberation. So let us substitute these things here. E equal to 10 to the power 6e times e to the power minus VA capital T over 4b. Mark it. Here capital T, you know, this is time of reverberation or period of reverberation. Okay. So now this E and E will cancel out, and you can see this can be written as e to the power VAT by 4b equal to 10 to the power 6. And therefore, VAT over 4v is ln 10 to the power 6. So this is 6 log 10 to the base E. But you know, at the base E, at the exponential base, log 10 is 2.303. So this is 6 into 2.303. And therefore, what will be the period of this reverberation? This will be, when you will simplify it, 6 into 2.303 into 4, that will be 55.27 times V divided by VA. So this is expression for the period of reverberation or time of reverberation. And actually this is known as what? This is known as Sabin's formula. Sabin's formula. Okay. In fact, here this constant, which I have written 55.27, if you omit that, and also this velocity v, because you know velocity of sound has a particular value in a particular medium. Okay. And if we are talking in the sound propagating inside a room, inside the room there is air, so we will talk about the velocity of sound in air, which has a constant value. Okay. So in this equation 55.27 divided by b, that constant is replaced by k, and so you can say that T equal to k times capital V over A. You know, capital V is the volume of the enclosure, A is the total absorption power. Okay. So I have written here, you can see K equal to 55.27 by V. V is velocity of sound. Now, if you take a velocity of sound in air in foot per second as 1100 foot per second, then you will obtain the value of k, and that will be this much, k equal to 0.05. And if you will take in SI unit the velocity v, which is 344 meter per second, then you will get k equal to this much. Okay, k equal to this much. So you can, in that condition, write T equal to 0.05 V over A. Okay, in this condition. And in this condition, you can write T equal to 0.16 V over A. So these are nothing, these are simply the Sabin's formula or Sabin's law. Okay. So I think now the idea regarding this acoustics of building, particularly this Sabin's formula, is very clear to you. Okay. Thank you very much.